Okay, so what we can do here, because we have two equations. So first equation is that we have two equations, that is nebula square phi. Okay, so these are the two these inhomogeneous second order differential equations, or we can say that we're basically writing those four Maxwell equations in terms of that scalar and that vector potential phi and a. And these two equations are inhomogeneous because there is source charge is present, right? And second, these are second order differential equations, right? So what basically this Coulomb gauge tells us? So we are basically imposing that our lambda dot A should be equal to 0. Right? So as I already told you, if we have this vector potential, if I choose now this vector as A dash plus lambda phi. Okay, तो अगर मैं इसको शिफ्ट करूंगा from a to a dash plus lambda phi, so as I already showed you in previous lecture, so this will be a this electric field remains invariant. So we are imposing this condition that nabla dot a should be equal to 0, or in other words we can say that this a cannot be uniquely determined, right? So if we add some parameters, some constant parameters, so it has different values. So we are saying that this nabla dot a is our, it is our that Coulomb gauge condition. Okay, so let us impose this condition on first second order differential equation. So this will be equal to, right, because that nabla dot a is equal to 0, so second term will be 0, so ये बन जाएगा minus rho by epsilon naught. So this is the rule that which is called that Poisson equation. Okay, so because now it is very clear, because we decoupled, we removed that a condition here, right? So we can now say that because rho is our charge density, suppose we have a system of charges. तो अगर हमारे पास system of charges, we have a given distribution of charge in some system, right? And this has direct effect on phi, because अगर charge density change हो जाएगी, it will affect on the potential. So this is basically which is called as that Poisson equation, right? But I will add one more point here, that this phi is not enough to say everything about that electric as well as magnetic field, right? So if we revise that, our equation was, that was, if you remember, that that's E equal to minus lambda phi. Okay. So this was our other equation. So what it tells us? So अगर हम देखेंगे, if we talk about the electrostatics, so in electrostatics, so we can ignore the second term. But in electrodynamics, you cannot ignore the second term. So that means we can have its effect also. That's minus 1 by c. तो इलेक्ट्रोडायनेमिक्स में ये इसका इफेक्ट होगा वेक्टर पोटेंशियल, राइट? सो दैट मींस अगर हम देखेंगे what this term has effect on the charges. So this second term, this vector potential tells us that if we have this distribution of charge in a given system, so one charge has an instantaneous effect on another charge. जो उसके neighbor neighborhood में होंगे, so it has its instantaneous effect on another charge, right? So that means this term, second term, that vector potential. So that means this charge has instantaneous effect on the nearby neighborhood charge. So but that violates our basic postulate of special relativity. तो हमको पता है कि जो special relativity, nothing can travel greater than the speed of light. Okay, so that means it violates the theory of special theory, these basic postulates of special theory of relativity, right? So, so in order to get rid of that, because this electric field, it has some delayed, it's some delayed quantity you can see here. Because if you have some charge, it has effect, and if you want to transform, if you want to see this change at some in some another frame of reference, so there will be some time delay. Or you want to calculate electric field at some point, or it sends information from one frame to another frame. So that means our electric field, it is we can say it's the delayed quantity, you can say, right? Now this is clear in this. So this is our first second order differential equation. So let's have a look on the second order, this second inhomogeneous differential equation, right? So second inhomogeneous differential equation tells us that okay. So second equation, let's have a look. Let us impose this condition that nabla dot A should be equal to 0, right? So we can rewrite the second order, this second differential equation. This can be equal to of A minus, or can I have this as, okay? But how we can calculate? But I think so. This equation is very difficult to calculate its solution, right? But हमें already पता है कि when we impose this Lorentz this Coulomb gauge condition on first second order this differential equation, तो यहाँ से हमने क्या लिया था? So we basically get this one, that nabla square phi equal to, so which is our Poisson equation, right? So we can calculate phi from here. So the solution will be some phi will be equal to 1 by c integral of rho d3x upon some, or I don't remember exactly, right? So the solution will be of this form. So you can check. So that means हमें phi पता है यहाँ पे, right? So phi you can substitute it here. So when you substitute phi here, so we can calculate A. So one more point. So this delta is our, it is that, so this is called a de motion. This is called a de operator. So de operator is nothing. It is simply a Laplacian operator. ये Laplacian operator ही है, but in 4-dimensional space. Because this is our Laplacian operator in 3 dimension and this is our time component. So that means when we have 4-dimensional space, Minkowski space, so we are using this D'Alembert operator here. So because so when we talk about this our Minkowski matrix, right? So that it can have time component can be negative, rest of space components will be positive. So that's why it is minus here. So this corresponds to our 3 space components, right? So this is how we can calculate, because यहाँ से जब हमें phi पता होगा, when we have already calculated phi from there when we impose that Coulomb gauge condition to this differential equation. तो यहाँ से हमें phi आएगा, then we can substitute that phi in this equation, because when we know phi, and we can have current density known, so we can calculate the value of A, right? So this is the way how we can impose some conditions like some gauges in order to simplify our problem. Because जो हमारी differential equations थी, those were coupled differential equation in terms of phi and A. So in order to decouple them, उनको separate करने के लिए we are choosing some kind of that conditions. So one condition is that's called Coulomb gauge condition, right? So in coming lecture, I will also discuss about what is Lorentz gauge, how it basically helps us, so how it helps us to solve some of the equations, or how it helps us to determine this electric as well as magnetic fields, right? So hopefully that we will discuss next lecture.